Welcome to another Explainer. Today, we're diving into the literal blueprint of ISRO's most ambitious project yet, the monumental construction of the Bharatiya Antariksh Station. You know, decades ago, Dr. Vikram Sarabhai had this incredible vision for a space program that would be entirely self-reliant, built from the ground up to serve the nation's most critical needs. Well, what we're looking at today is the ultimate culmination of that exact vision. We're tracking the journey from those foundational early studies all the way to the actual construction of a permanent human habitat in low Earth orbit.
To really wrap our heads around the sheer scale of what India is building here, we have to start with this massive number, 50 tons. That's the total expected weight of the fully assembled orbital habitat. To put that into perspective, imagine a fully loaded commercial airliner, but completely assembled in the brutal vacuum of space. For a space agency that built its entire reputation on lean, hyper-efficient robotic missions, putting a 50-ton structure into orbit is an engineering leap of staggering proportions.
So here is our roadmap for today. We'll cover the BS blueprint, semicryogenic muscle, SpaDeX precision, structural armor, and wrap up with the self-reliant future. Let's jump right in. Section 1. The BS blueprint. Visualizing the 5-module station.
The overarching vision for this station gained massive momentum with the Union Cabinet's historic approval back in mid-September 2024. And it wasn't just a green light, it was a full-on mandate, extending the Gaganyaan program to officially transition ISRO towards a sustained orbital presence. Moving from that 2024 mandate, ISRO is now on a highly accelerated path to launch the very first module, BA-01, by 2028. From there, the assembly sequence is going to meticulously build out the infrastructure, leading up to a fully operational 5-module space station by 2035.
The architectural philosophy behind this is absolutely fascinating. We're talking about 5 autonomous modules designed to operate with minimal human intervention. But listen, this isn't just some isolated laboratory floating up there. With docking ports fully compatible with the International Space Station, it is wide open for global collaboration. It's actually designed to serve as an interplanetary transfer hub and a fuel depot for future deep space missions. It even paves the way for commercial suborbital space tourism. It's a true multi-purpose orbital port. Now, to get this monumental project off the ground, the initial budget allocation is 1,763 crore rupees. In classic cost-efficient ISRO fashion, this highly focused allocation covers the entire development and launch of that first module, BAS-01, over a tight 4-year period from 2025 to 2028. Basically, this funding handles the immediate system engineering and those absolutely critical technology validation missions we need before we ever put humans aboard. Section 2. Heavy lifting. The semicryogenic breakthrough.
Okay, here's the stark reality of orbital mechanics. You simply cannot assemble a 50-ton station in orbit without a serious heavy lift vehicle. You've got to push massive, dense modules through the atmosphere. So ISRO is solving this by replacing the current liquid core stage of the LVM-3 rocket, the L-110, with a brand new semicryogenic stage, the SC-120. By switching to liquid oxygen and space-grade kerosene, they're bumping their payload capacity into high-altitude geostationary transfer orbits by a full ton, taking it from 4 tons to 5. And that extra ton? That's the exact margin needed to loft these heavy habitat modules.
Delivering that much-needed extra muscle is the newly developed SE-2000 engine. Make no mistake, this is an absolute beast of an engine, putting out 2,000 kilonewtons of thrust. It operates with a highly complex, oxidizer-rich staged combustion cycle at a crushing chamber pressure of 180 bar. To put that into perspective for you, that is like the immense pressure you'd find deep at the bottom of the ocean. This is a tier of rocket engineering that only a very select few nations have ever mastered, requiring highly specialized materials to withstand intense temperatures and an incredibly reactive environment.
Of course, you don't just build a beast of an engine like this, hit the ignite button, and cross your fingers. Rocketry requires rigorous step-by-step validation to prevent catastrophic failures. ISRO's Liquid Propulsion Systems Center stepped through single-element tests, then the preburner ignition test, culminating in a major breakthrough just recently on March 28, 2025. They successfully pulled off a 2.5-second hot test of the powerhead test article at Mahendragiri. That test successfully validated the critical turbopumps and preburners, basically clearing the runway for the fully integrated engine.
Section 3. SpaDeX precision. Threading the needle in orbit. Once we muscle these heavy modules into space, brute force immediately gives way to extreme finesse. To actually connect them together, we look to the Space Docking Experiment Mission, or SpaDeX, launched in December 2024. SpaDeX is a 2-year technology demonstrator mission that deployed 2 spacecraft, the Chaser satellite and the Target satellite, into a 470-kilometer orbit. The mission design here is wild. They intentionally drift apart, and then they have to use advanced sensors and propulsion systems to autonomously find each other and reconnect, closing distances from 20 kilometers down to just 3 meters.
The secret behind their connection is the Bharatiya docking system. This is an indigenous, low-impact mechanism, but more importantly, it's completely androgynous. What that means is the docking interfaces on both the chaser and the target are identical. This ensures incredible flexibility because any module can dock with any other module without needing specific male or female adapter configurations. That is absolutely vital for station assembly and future crew transfers.
Now, here is the ultimate, mind-bending challenge of docking: the speed difference. Both spacecraft are hurtling around the Earth at an orbital velocity of 28,800 kilometers per hour. Yet, to dock safely without destroying each other, they must slow their relative speed down to just 0.036 kilometers per hour. That is a mere 10 millimeters per second. It is literally the orbital equivalent of threading a needle while riding a bullet.
Section 4. Structural Armor. Surviving the Space Environment.
Getting the mass to orbit and docking it together, well, that's really only half the battle. The station then needs to survive the brutal extremes of the space environment for over a decade. Carrying forward Dr. Sarabhai's legacy, the Vikram Sarabhai Space Center is leveraging India's top academic research to develop next-generation materials. Through ISRO's Respond basket, academics are developing functionally graded polymer sandwich cores, which are essentially high-tech shock absorbers designed to handle micrometeoroid impacts. They're also using generative AI to design hyper-optimized structures and developing refractory concentrated alloys that act like ultimate heat shields, sustaining operations at temperatures well over 1,400 degrees Celsius. You can see how incredibly specific these research initiatives have to be. For example, there's a VSC proposal targeting ultra-low infrared emissive and solar absorptive thermal control coatings. In the vacuum of space, without air to distribute heat, the temperature swings are incredibly violent. These specific chemical coatings essentially act as both sunscreen and heavy-duty insulation, ensuring the station can withstand intense, unfiltered solar radiation without baking the crew or the electronics inside. In space architecture, mass is absolutely everything. Every single gram you can save on advanced thermal coatings or impact-resistant polymers directly dictates the ultimate feasibility of the station. Lighter structures mean you can launch more scientific payloads, more robust life support systems, and more fuel. It's that simple.
Section 5. The Self-Reliant Future. Microgravity and Beyond.
So, why invest billions and dedicate a decade to building this whole thing? What does it actually mean for the future of India's space vision? Well, the station will serve as a premier microgravity laboratory. That lack of gravity allows for total breakthroughs in space biology, advanced pharmaceutical development, and manufacturing ultra-pure materials that will directly revolutionize medicine and technology back here on Earth. And equally important, the technologies validated here, the life support, the docking, the semicryogenic heavy lift, these form the exact blueprint required for the Chandrayaan-4 sample return mission and eventually putting Indian astronauts on the moon. From Dr. Vikram Sarabhai's initial vision of an independent space capability to the assembly of a 50-ton orbital habitat, the progression is it's nothing short of astounding. By mastering heavy lift, precision docking, and advanced materials, India is firmly securing its permanent foothold in the cosmos, leaving us to wonder, with the Bharatiya Antariksh Station actively laying the groundwork today, just how quickly will these indigenous building blocks turn science fiction into our interplanetary reality?